This video is going to be the start of the fluids topic, and it's going to be about density and pressure. Density, which we'll represent with the Greek letter rho, is the ratio of the mass of a substance to the volume of that substance. The equation for density is equal to the mass, m, divided by the volume that substance takes up. Pressure, which we'll represent with the symbol P, is the ratio of the perpendicular contact force, which sometimes we call the normal force, per surface area. The SI unit of pressure is expressed in newtons per meter squared and is equal to a Pascal, PA. So if I have a disk of surface area A and I apply a perpendicular force to that surface, the pressure on this disk is equal to the force I applied, perpendicular, divided by the area of the disk. Now let's expand our thinking about pressure to pressure involving fluids. I'm going to make a cylinder that sits inside a fluid so that the top of the cylinder is at the top of the fluid and it sticks down into the fluid like this. The cylinder is going to be height h from the surface of the fluid, and the cylinder is going to have a cross-sectional area A. Now we can use this to find a relationship between the depth you are in the fluid and the pressure you feel. So let's assume that our cylinder has a weight that's pulling it downwards, and we know that weight is equal to mass, the mass of the cylinder times the acceleration of the gravity. And we can expand mass out by saying, no, we have the density of the cylinder times the volume of the cylinder times gravity. And we can expand the volume out further by saying the area of the cross-sectional area times the height of the cylinder is the volume. Okay, so we have all these terms which tell us something about weight. Now, because our cylinder is neither accelerating upwards or downwards, we know it's in translational equilibrium, which means that the pressure of the fluid at the bottom of the cylinder is pushing upwards with the same force. And we know pressure times area is force, so the weight is equal to the force of the fluid, which is the pressure times the area of the fluid surrounding the cylinder. We can substitute for weight what we just did before, and we see that the area of the cylinder is on both sides, so that goes away. And if I collect like terms, I see that the density of the pressure I have is equal to the density times the acceleration of gravity times the height that the fluid, the height of my object in the fluid. Notice that the pressure increases only with depth. The density of the fluid and the acceleration of gravity are relatively constant. So only how deep you are in the water, or in the whatever fluid you're in, determines the pressure. It has nothing to do with the shape of the object itself. One thing I didn't include in our original calculation was the fact that at the top of the cylinder, which is sticking just at the surface of the water, there is an atmospheric pressure, which we'll represent with P naught. So really, the pressure at that depth h in the water is not only due to the fluid, but it's due to the fluid's pressure plus the atmospheric pressure which sits above. So now we have a complete equation which describes how pressure changes with depth. Okay, just to drive my point home further, if I were to take a really irregular shaped container containing a blue fluid like I've drawn here, and I were to draw lines across this container at different heights, as I would go from the top line to the bottom line, I would feel increased pressure, but everything along that line would have the same pressure because it's at the same height from the surface of the fluid. So any point along this line would have the same pressure, as would be true for this line and this line. So just a few more things about pressure of an object. If I have an object, its weight is pulling it down in the fluid, and the reaction force of the fluid is pushing it upwards. Remember, this is sometimes called the normal force. So if the object is stationary in the fluid, the weight of the fluid equals the reaction force of the fluid below. The pressure always generates an upward force equal to the weight. So the weight equals the reaction force We can expand out the weight, and we can expand out the reaction force to be pressure times area. Area is in both terms, so we can cancel that out. And we see that pressure, once again, is equal to the density times gravity times the depth that the object is submerged. So up to this point, we've assumed that the forces are equal. What if the forces aren't equal? Well, if the forces aren't equal to each other, then we have a situation where the fluid will flow to equalize the difference in pressures. And flow is what we'll talk about later in this topic. All right, that's the end. Sorry, that's the end.